The final paper in this session is Retina, analyzing 100 gigabit Ethernet traffic on commodity hardware. This paper will be presented remotely by Jerry Won, who will be online, and we have Zakir to answer questions after the talk. Jerry is a fourth-year PhD student at Stanford University, advised by Zakir Durmirich. His research interests are in computer networking with a focus on network performance, measurement, and security. He enjoys building systems for high-speed traffic analysis, efficient routing, and using large-scale data to understand complex network ecosystems. The artifacts associated with this paper have been evaluated as reproducible, and the code is available on GitHub if you want to try it. Roll the video, please.
Hi, everyone. My name is Jerry Won, and I'll be introducing Retina, a new framework for analyzing 100 gig traffic on commodity hardware. This was joint work with Fengchen Gong, Tom Barbet, and Zakir Durmirich out of Stanford University and UC Louvain. So over the years, network speeds have been increasing dramatically. Today, it's common to see 100 gigabit per second networks, and even faster line rates are coming soon. However, while production network speeds have gone up, network monitoring and measurement tools haven't kept up pace. The sheer volume of traffic from a 100 gig link overwhelms most analysis tools, making the possibility of answering even basic questions about high-speed network traffic extremely difficult. Popular tools like Zeek, formerly known as Bro, and other network monitors are fantastic tools with expressive interfaces that have worked well in the past, but unfortunately don't scale well to today's high-speed environments. On the other hand, high-speed switches, routers, and packet processors lack the expressiveness needed to answer arbitrary questions about network traffic. Because of this, people still struggle with analyzing network traffic at 100 gig line rates. One solution is to use specialized hardware like FPGAs, smart NICs, GPUs, or commercial appliances to help offload compute-heavy tasks. But these devices are expensive and difficult to program for most network operators and researchers. Alternatively, many people have also spent months building custom analysis tools from the ground up. But this approach is extremely tedious and error-prone, and not to mention isn't very flexible. So today, I want to introduce Retina, a software framework that enables operators and researchers to ask complex questions of 100 gigabit per second network traffic using a single server and no specialized hardware. For example, in just 10 lines of code, we can log the server names and cipher suites of all TLS handshakes with Netflix domains from a 100 gig link in real time. Something like this would be tremendously useful for investigating security properties of video streams or understanding performance characteristics of Netflix traffic. So now performing high-speed traffic analysis no longer requires programming a smart NIC, writing Verilog, or spending heroic efforts building a custom tool. It involves writing some general purpose analysis code and then running it on a single commodity server in a standard server NIC. The Retina framework uses a simple subscription interface that lets users request a callback on a subset of traffic on a network. And these can range from raw packets to reassembled connections to parsed application layer sessions. So subscription consists of a filter and a callback. Filters are similar to Wireshark display filters and let users specify the traffic of interest, while callbacks specify some custom analysis logic that's written in normal Rust code. And what this does is it allows arbitrarily complex processing without the restrictions of a domain-specific language or a query interface. And then the framework will then take care of efficiently processing high-speed traffic to fulfill the subscription so users can focus on core analysis logic without having to worry about hardware specifics or low-level optimizations. So before I get into how Retina works, let's first take a look at what a typical traffic analysis pipeline might look like. So imagine you are a network operator or a researcher who wants to answer some question about your network traffic. Now, this could be something like, what is a download throughput of video streams from Netflix, or what is the distribution of supported cipher suites advertised by TLS clients, just to name a few. So there are a couple things you need to do, right? You start with raw traffic on the wire, which you first need to get physical access to using the network interface, and then read the packets into memory using some sort of packet capture technology. But raw packets usually aren't enough to gain any substantial insights. There's more work that has to be done to track and reassemble connections. And if you want to reason about higher level entities like application layer constructs, you would also need some way of performing layer 7 parsing. And then finally, once you've parsed out the data that you're interested in, you might run some analysis logic to produce your desired result. And while there's been a lot of progress in optimizing each of these individual steps, it still takes tremendous amounts of effort to implement each component and then piece them together in a way that can efficiently process 100 gig traffic for a variety of different use cases. So in building Retina, what we observed is that many analysis questions typically focus on only a subset of network traffic. And this allows us to prioritize computation for the desired analysis task. And we designed Retina following two main principles. The first is eagerly reducing the volume of traffic that needs to be processed at each step. So for example, this means minimizing the number of packets that need to be brought into memory, or minimizing the number of connections that need to be tracked. The second is lazy data reconstruction, or in other words, delaying the execution of expensive processing operations until we know that they're necessary. And this contrasts with the way many classic network monitors work, which emphasize full inspection of all traffic as soon as possible. So while this makes sense for intrusion detection, it results in wasted work on things that might not actually be of interest in other contexts. So how do we actually minimize the amount of traffic that needs to be processed? It turns out that there are actually many opportunities to discard traffic at every layer of the processing pipeline, even for a simple subscription. So what we do is we decompose user-specified filters like this into multiple layers, starting with an on-NIC hardware packet filter, followed by a more expressive packet filter in software, a connection filter, and an application layer session filter. I want to emphasize that this hardware packet filter is placed on a standard server NIC and not a smart NIC. By eagerly discarding out-of-scope traffic throughout the entire analysis pipeline, Retina minimizes the total volume of traffic that needs to be processed by subsequent analysis steps, prioritizing resources for relevant network traffic. But with multiple filters now being applied, we need to make sure that each of these execute quickly while the filter language remains user-friendly. And we do this through what we call compile time filter generation, which leverages a metaprogramming feature of Rust called procedural macros. At compile time, Retina will parse and transform the filter expression into native Rust code that implements each software subfilter. These are then statically verified by the Rust compiler and then inlined into each processing layer, which prevents the overhead of interpreting filters at runtime. The second half of Retina's design is lazy data reconstruction, which goes hand in hand with multi-layer filtering by deferring processing operations in order to avoid wasted computation on traffic that might be discarded by later filters in the pipeline. So to demonstrate this, I'll discuss Retina's mechanism for stateful application layer parsing, but you can refer to the paper for details on other components like stream reassembly or connection tracking. So Retina uses a subscription-specific state machine where the framework automatically derives state transitions according to the filter and the subscribed data type. So as an example, let's take a subscription for TLS handshakes where the server name matches Netflix. In this scenario, Retina first performs stateless probing of incoming packets for TLS protocol messages, and then applies the connection filter to drop non-TLS connections. So here, we can stop processing traffic mid-connection if the filter doesn't match, preventing the need to further reassemble packets from these irrelevant streams. The framework will then continue parsing the remaining connections until it can filter on the server name field of the handshake. And this can happen as early as the fourth packet in the connection. And since we're only interested in TLS handshakes, there's no reason to continue tracking the connection after the session filter, so the entire connection can then be dropped and subsequent packets will be immediately discarded. So these state transitions you see here are automatically derived at compile time to prevent redundant parsing in stream reassembly, allowing Retina to accommodate large volumes of traffic while still remaining flexible over different subscription types. So now let's take a look at some evaluation results of our framework by looking at the maximum traffic rates that can be achieved with no packet loss. So of course, this value is going to heavily depend on the filter, the complexity of the callback function, and the actual network traffic itself. But to mimic Retina's target use cases, we decided to evaluate Retina's performance on live traffic from a real network. So in this figure, I'm showing the results from a subscription to all TLS handshakes on a campus network with no hardware filtering enabled. So on the x-axis is the number of cores used to process traffic, and on the left y-axis is the average throughput sustained with 0 packet loss, where higher means better. On the right y-axis, I've shown the approximate packets per second using average packet size, and the different bars represent varying callback complexities in terms of CPU cycles. So as we can see, with just 8 cores, Retina can support well beyond 100 gig traffic rates, even while running heavy callback loads on fully parsed TLS handshakes. In fact, for values above this green dashed line, we saturated our input link with 0 loss, so they actually represent a lower bound on what we can achieve on our network. Other throughput results for other types of subscriptions can be found in our paper. To show how multi-layer filtering affects processing throughput, we also measured the percentage of incoming packets that triggered each processing stage. So you can think of this as the frequency that each stage needs to run. So with our example of a filter for TLS connections to Netflix on port 443, 100% of packets will hit the NIC interface, and then the hardware filter reduces the fraction of packets that need to be read into memory down to 35%. In this case, since the hardware filter is able to implement the entire software filter, the software filter actually just acts as a pass-through, and these 35% of packets will require lookup or insert into a connection table. However, only 0.4% of packets will ever need to be fully parsed. And while this might seem like a surprising reduction, the reason for this is that the connection filter will eliminate non-TLS connections as early as the client hello, and the session filter will also work to remove non-Netflix connections as soon as TLS handshake parsing completes. And then any subsequent packets from these discarded connections never have to be parsed. So the end result is that the custom analysis logic, which might contain some expensive code, only needs to run on a tiny fraction of the input traffic, lowering the average end-to-end per packet processing rate, processing time. So at this point, we know that Retina is able to support high network speeds and provides a simple interface for users to perform traffic analysis. So what are some things that we can do with Retina that we couldn't do before? One example is investigating cryptographic anomalies that can only be detected through large-scale passive network analysis. So TLS traffic makes up a large fraction of the internet today, and part of the handshake protocol involves the client sending a 32-byte nonce called a client random. A fundamental assumption is that the likelihood of observing repeat values should be exceptionally low, since these are randomly generated 32-byte values. But using Retina, we were able to write just 40 lines of code to subscribe to all TLS handshakes on the network, and then measure the frequency of distinct client randoms. And this allowed us to discover thousands of repeated nonces in just 10 minutes of monitoring a 100 gig network, which hints that TLS nonces are probably not as random as we come to believe. So in conclusion, Retina lowers the barrier to entry for high-speed traffic analysis, making it possible to support 100 gig traffic rates using a single Commodiy server and writing a few lines of Rust code. It uses a simple subscription interface that is compiled into an optimized analysis pipeline that uses multi-layer filtering and lazy data reconstruction to prioritize relevant traffic. And we've also explored one case study where Retina can be used to easily uncover cryptographic anomalies in network traffic that would otherwise be extremely difficult to observe. Retina is publicly available at this GitHub repository, and we invite everyone to try it out. Ultimately, we hope that Retina will be a useful tool that enables future research and other possibilities that we haven't yet thought of. So thank you for listening, and please get in touch if you're interested in.
And we have Zakir on stage to answer questions live. So if you have questions, please raise your hand so we can find you.
Hello, this is
Anja
Feldmann from Max Planck Institute for Informatics in Germany. I do know Bro quite well and have worked with it extensively. And one of the big things of Bro is, of course, the fact that you can do some auto-configuration. You can do extensive filtering to slow down the amount of traffic that you have to analyze, etc., etc. So could you elaborate a bit more why your tool is so different from Bro or Zeek, how it's called these days?
Sure. So I think a lot of this comes to not trying to reassemble everything. A lot of it is discarding a lot of traffic along the way.
But Pro does the same thing. You can say, just give me TLS, or just give me certain ports. So you filter out all that traffic up front.
So
Whatever isn't needed isn't captured.
So that traffic may not be exported to the user, but it does still make it through a significant portion through the processing pipeline. And we work directly with the developers of Zig. And so maybe we want to get in touch with them. We can dive into that deeper. But this was in collaboration with them that we did that experiment.
The other question I have is, if a user submits a query, how do you estimate what fraction of the actual traffic you need to take a look at?
So we don't necessarily estimate. That's something you're not going to know until you actually run the experiment. So this is something we imagine in the hands of researchers. They have an experiment that they want to go off and perform. But it's hard to tell ahead of time necessarily what percentage of packets will necessarily match each filter. And it may be something that your CPU actually can't handle 100% of it, and it's something that you have to do flow sampling in order to actually be able to essentially achieve that callback for everything that matches that filter.
So how would you feed that back to the user, given that you're saying that...
I wanted to ask the same question.
Sure. I mean, what we can look at is like packet drop rates, or where things are spending time in the framework. So if the CPU is something that is completely used up trying to meet all these filter stages, what we'll say is that we're dropping packets essentially in this framework along the way. We know we're not able to completely achieve what the user essentially is asking for, and at that point they can decide to downsample the traffic. At that point we can downsample the flow level, for example, to look at a certain percentage of TLS flows that are going by.
Other questions from the audience? I have a question. How steep would you say is the learning curve? If let's say I have some basic Rust knowledge, how steep is the learning curve for me to use this?
Yeah, I mean, part of it's in Rust. Rust is not necessarily the easiest programming language on earth, but it is a standard programming language. I think that folks are starting to use more. We try to keep the filter language itself pretty close to what Wireshark looks like, to what a BPF filter looks like. Our hope is that that is something that feels natural to folks. But writing the callback, you do have to write some code. I would say if folks are having trouble, we'd love to talk to you. We'd love to figure out how to make this as easy as possible. So if you're running problems, get in touch. I think that's on many ways for us as the framework to developers to figure out how to make that as easy as possible.
Okay. Any more questions from the audience? If not, let's thank the speaker and thanks Zakir. And enjoy lunch.